result. Yeah, the talk will be about some recent results in sort of investigating certain fractal properties that a class of planar growth models are supposed to exhibit. So I'll start the talk in sort of setting up a sort of a general question, but then we'll sort of specialize to a particular setting, which allows one to really analyze things in a rather refined sense. And throughout the talk, please feel free to stop me, ask questions. I am usually sort of monitoring the chat, so you can sort of also sort of ask a question there, or I would sort of encourage you to actually sort of ask it out loud. All right, and the results will be sort of based on various joint works. I'll mention the co-authors as we go along. All right, so broadly, so there are different sort of paradigms of stochastic growth, and the kind of models that we'll sort of be talking about basically have some characteristic features. And so, okay, we don't have to sort of look at it very closely, but broadly speaking, some of the features that these models share are, like it's the growth. So this will be basically, you can think of as a function sort of evolving in time. So you should think of a one-dimensional function, and then time is sort of in the vertical direction. So in some sense that leads to a two-dimensional model. Okay, so this function or the interface that grows in time should have some features. One of them is that the local growth is given by slope-dependent speed, usually a nonlinear function of the slope. And then, however, so this is sort of local behavior, but then also there is some global smoothing happening, and the growth is stochastic. So the growth is driven by sort of local random noise. Okay, so basically three features: some global smoothing, some local roughening due to the random stochastic noise, and the growth speed is sort of also function of the local gradient. And typically one should expect that to be depend in a nonlinear way on the local gradient. And it turns out that as long as you have these features, general class of models given which share this set of features are supposed to all behave in the same way. And those are sort of supposed to all lie in a sort of universality class, which is governed by a characteristic stochastic partial differential equation, which was sort of proposed by physicists Kardar-Parisi-Zhang. Okay, and so this sort of this is why this universality class goes by the name of KPZ universality class after the name of this three physicist. All right. Okay, so sort of I'll sort of mention one canonical model here. So this is many people might be already familiar with this in the audience. So forced passage percolation. So this is essentially okay. So let's sort of maybe define it somewhat precisely. So let's say you have Z2. The lattice, also you can sort of make sense of this in the continuum. So let's say you have the lattice Z2, and then let's say you're on the vertices or the edges of the lattice, you put some random weights. So the idea is to distort the graph. So Z2 is a graph equipped with the L1 distance. So you can look at the nearest neighbor graph on Z2. So this is a metric space, but now let's say you put a weight on each edge. So each edge comes with a weight. And you should think of this weight as being the new length of the edge. So previously the length was simply 1, but now this random weight is what the length of this is. And this actually gives you a random metric space, right? So this distorts the geometry of Z2 in some sense. And so somehow the object of interest is sort of to see how metric balls grow as you grow their radii. Okay, so we'll see our simulation soon. But any questions about sort of this model, although we will not study this eventually, but any questions about the definition? All right. Okay, so here is a simulation of the metric ball for forced passage percolation. So this is how the metric balls grow. The different colors indicate the different level sets. So points of the same color are basically the same distance from the origin under this random metric. So as you sort of see, if you zoom out, this sort of picture looks like a convex body, and it's actually supposed to. It's a theorem now that actually this is indeed true, that regardless of what the distribution of. So recall, so there is some underlying distribution, right? So you have this lattice. Every edge comes with a random weight. So these are, let's say, IID weights, but the distribution of the weight is something that I have not specified yet. And it turns out that this shape, this convex shape, depends on the precise nature of the distribution. However, interestingly, it's predicted that if you now zoom in on the boundary, so the boundary is going to be a rough random function-ish object. So if you zoom in and see the fluctuation of this boundary, that should be universal. That should really not depend on the precise nature of the distribution of these edge weights, as long as they're reasonably nice. Okay, so this is sort of the fluctuation theory is supposed to be universal. The law of large numbers is not supposed to be universal. Okay. So, okay, so once you have this metric ball, you can sort of try to understand metric balls from different centers, right? So the previous slide simulated the metric ball started from, let's say, the origin, but now you can have multiple sources and you can try to grow metric balls from them. And at some point they will interact, and you want to understand how the interaction happens. So how does the growth of this metric from different points interact with each other? Okay, so that's broadly something that we would aim to understand. However, it turns out that the model that I proposed, that I sort of mentioned, is actually extremely difficult to study. So it's most of these problems about this model are actually pretty open, and the progress has been rather minimal. Although there's been some impressive progress, but it's sort of so currently the state of knowledge is extremely far from what is supposed to be true. Okay, so what we will do instead is actually sort of change perspective slightly and actually work with a certain different class of models which are somewhat similar, but actually has the advantage of actually having some extra additional properties, which allows one to sort of really sort of carry out a refined investigation of those models. Okay, so more broadly, the models that I'll sort of now indicate or mention have some certain algebraic properties, and that allow you to use tools from things like random matrices, algebraic combinatorics, and so on. And then you can use those as inputs and then sort of do some probabilistic analysis to answer some of these questions. And so study of such models actually goes by the name of integral probability. And so the talk will not be too much about integral probability. It will essentially use some input from there, but then mostly carry out a probabilistic analysis. Okay, so what is the model? So I'll just mention two models. So again, the point is we should not focus too much on the model. We'll eventually sort of focus on a particular universal object that all of these sort of discrete models are supposed to converge to. But let me just sort of start by sort of actually highlighting what is the difference between last passage percolation and forced passage percolation. So in last passage percolation, again, let's say you take Z2 as we did in the previous model. Again, you have let's say random weights on the vertices. So each vertex comes with a random weight. And now instead of looking at the random metric space that it gives you, now let's say look at any 2 points. Oops, sorry. Yeah, you look at any 2 points, let's say this one and this one, and you look at an oriented path, which only, let's say, goes to the right or north. And for each such path, you sum up the weights along the path, okay? And what you're interested in is actually look at the path which maximizes the weight. So if you sort of think about it a little, in the previous model, when we were looking at forced passage percolation, which was this sort of random metric space, essentially what you were doing was you took 2 points, you looked at all lattice paths, all possible lattice paths, no orientation constraint, something like this. It should be self-avoiding, but and you summed up the weights along the path and minimize that weight, right? That's what a metric space looks like. So this path would be somehow the shortest path in this random weighted version of Z2. However, in last passage percolation, you simply restrict yourself to oriented paths and you maximize the length instead of minimizing the length. Is the definition or the distinction between the two models clear? And it turns out that there is also a variant of such discrete models, which is semi-discrete, where you have, let's say, instead of having Z2, you have, let's say, a bunch of copies of the real line. And now instead of having random weights on vertices, you have some function on each copy of the real line. Okay, so it's some function. And now, if again, similarly, as here, you take an oriented path. So you should think of this as an oriented path, maybe. And for each path on this side, the length of the path or the weight of the path was simply the sum of the random variables along the path. Here, what you do is you look at this path, and the weight is basically the increments of the functions along this path. So you take this function, look at its increment along this segment, then add it to the increment of the second function along this segment, and then basically sum them up. So you can think of this as sort of a semi-discrete limit of this guy, where the discrete thing in this direction has sort of been taken, have been passed to the limit, and you obtain a real line. Okay, and again, just to sort of set up a term, we'll call this maximizing paths as geodesics, although that's sort of slightly an abusive terminology because typically geodesics are used to denote shortest paths. And so, but we'll sort of use the same terminology in this setting as well, where paths are actually length maximizing. Any questions? Okay, so it turns out that, so in the previous slide, I described as discrete LPP, last passage percolation model. We'll call that LPP for last passage percolation. So we described a discrete LPP model and a semi-discrete LPP model. And it turns out that if you now pick your random variables or the distribution of the variables carefully, then it turns out that these models are exactly solvable, or actually, in other words, admit some algebraic connections. So in the discrete setting, recall the model looked like this. So if you pick the variables that are IID on the vertices as, let's say, exponential or geometric, then you get some nice structure here. Similarly, on this side, if these functions are taken to be IID Brownian motions, or two-sided Brownian motions, then also you get something very nice. So that's what this slide indicates. So if you, in the discrete world, if you pick the random variables that drive your LPP model to be either geometric or exponential, and in the semi-discrete world, if you pick them to be Brownian motions, then you actually, the models actually have connections to many algebraic objects, in particular to say things like eigenvalues of random matrices, which can be analyzed using other tools. This then can be fed into the analysis of these models, because that's basically the algebraic connection that one exploits. However, it's important that the model, that the random variables have these special distributions. These connections disappear as soon as you port up them a little bit. So it's a very fragile sort of setup. Okay. So, okay, so instead of sort of working with so many models, what we will do is we will sort of work with a scaling limit of this model. So we'll work with the limiting random energy field. So instead of working with individual models, we'll consider a scaling limit, which was recently constructed in 2018 by Dauvergne, Ortmann, and Virag. So what do I mean by that? So it's actually going to be like, you should think of, so there's some space, scaling of space and time and whatnot. So usually what will happen is now you should think of as two real lines, let's say two copies of the real line. So let's say one endpoint varies here. So right, so on the lattice, you had some point here and some point here, and you were looking at some, okay, let me use a different color. And maybe you were looking at some best path between these points. However, if you take the limit, you should think of this point as now varying continuously on this line, and this point as varying continuously on this line. And S phi x is sort of the scaling limit of the weight of this path, and the blue curve is you can think of this as the scaling limit of this green discrete path. Okay. So this is sort of a continuum model that we will sort of study, which is supposed to be the scaling limit of all these models, regardless of whether they are exactly solvable or not. However, it also is possible to vary the heights of these points, right? So here in the picture that I just described, y was varying on this line, x was varying on this line, but you could also vary y in the vertical direction and similarly x in the vertical direction. So to define some notation, so L, ys, xt should be thought of as the scaled weight from ys to xt. Okay. So in this picture, s was taken to be 0 and t was taken to be 1, but you can also vary the height. So this is why it's like you should think of this as, let's say, a spatial direction, and this should be thought of as a time direction. Okay, so it's like a 4-parameter random energy field, which is supposed to be the scaling limit of all these discrete or semi-discrete LPP models. Again, any questions about the setup? So this is what we will study. Okay. All right, so just to sort of point out some properties. So if you fix again the heights to be 0 and 1 and vary the points y and x, but let's say for the moment just fix y and vary x. So you can plot the distance from y0 to x1 as x varies on this copy of the line. So that will plot out a function, right? So if you plot the distance, that will be a function on this line. So it turns out that that function globally looks like a parabola. Okay. However, it's a random function, so it will have some fluctuations on top of this parabola. Okay, so it turns out that this fluctuation, the green process, is stationary, and it goes by the name of Airy-2 process. Some of you might already be familiar with this. So it's a stationary continuous process, and it has if you look at the 1-point distribution of this green process, it's given by what is known as a Tracy-Widom distribution, which also arises as a limiting distribution of the largest eigenvalue of a random Gaussian matrix. Okay, so this is sort of, and you already see sort of how the algebraic connection sort of manifests itself. Okay, so one thing to keep in mind, if you fix one endpoint and vary the other endpoint on a line, then you get something reasonably nice, which is this parabola plus some fluctuation on top of that, which is stationary and continuous. Okay. Again, but like, so I recall the initial slide that I had where I was sort of looking at growth of the metric ball from two sources. So a version of that in this setting would be you pick 2 points here, -1, 0 and 1, 0, and you draw this sort of function centered at these 2 points, right? So both of them look like, by stationarity of the model, both of them look like parabolas rooted at these 2 points. And you have fluctuations on top of them, and the fluctuations are coupled now. Okay, so each of the individual green fluctuations we know from the previous slide. Sorry. Yeah, so we know from the previous slide that from each given point, the function is a parabola plus some fluctuation, which is Airy-2. But now you have the same type of function, but now rooted at 2 different points. And so, of course, they are random functions, so they're coupled together. So you want to understand how what is this coupling? What is the coupling structure? Further, you can also, instead of varying the points here, you can also sort of see how the growth is coupled if you vary the time direction, right? So here here we are trying to see how growth is coupled when you vary the other endpoint on this line, but you could also vary it in the temporal direction, or just completely all over the space. So the broad goal is to sort of understand the coupling structure of the growth or the distance function rooted at these 2 points. Okay. Okay, so it turns out that there is a very nice function that one can sort of consider instead, which actually encodes a lot of this information. So this is what is known as difference profile, which was introduced in a paper of mine with Alan Hammond and with Basu. So what you do is simply, so what you do is simply do this. So you have 2 points, let's say -1, 0 and 1, 0. And you take some point xt in space-time. So what you do is you basically take the distance from 1, 0 to xt, and also take the distance from, sorry, what is happening with my iPad? And also take the distance from -1, 0 to xt, and you simply take the difference. Okay, so we want to understand how the passage times from these 2 sources are coupled. So one way to study that is to study the difference. We will see that this difference encodes a lot of information. Okay, so this is what we will call as a difference profile. So dxt is simply the difference of the passage times from this point to 1, 0 minus the passage time from this point to -1, 0. Okay, so is the object clear? What the object is? Okay, good. So this basically tries to this is sort of an observable that actually encodes a lot of information about how growth happens or evolves from 2 different sources. Okay, so now we will see how geodesics sort of interact and how that affects the difference profile. Okay, so this is sort of the first observation that typically geodesics coalesce. So what do I mean by that? So take a point xt as in the previous slide. Okay. Now you want to look at the best path going from xt to, let's say, -1, 0 downstairs or 1, 0 downstairs, right? Now, what is the geodesic doing? So the geodesic is trying to maximize its weight, right? So if you remember the original definition, between 2 points, I'm looking at the path which has the largest weight. So which means that both this path the purple path ending at -1 and the blue path ending at 1, they're both trying to maximize their weights, although their destinations are different, but their initial starting points are the same. They both start from xt. So it's sort of plausible that if there is a part of the region where there are some nice variables, in the sense that if the weight of the variables are quite nice here, actually, let me just draw another figure. So okay, so I have two paths, which one of them goes down to sorry, I mean one here. So I have two paths, one of them is going down to -1 and one of them is going down to 1, and they're both trying to maximize their weight. So if, let's say, the part of this region has some nice weights, so the values of the random variables in this part of the space is, let's say, very high, atypically high, then it's actually useful for both the geodesics to actually pass through this region. And so you see that if they both pass through this region, the initial part of the segment will exactly be the same, but because they eventually end up at different locations, they will eventually bifurcate. Okay, so the geodesics initially coalesce for a bit, they shared the same journey, and then eventually they sort of go on to their own ways because they want to end at different locations. Okay, so this is what I mean by geodesic coalescence. Is the phenomenon clear and why it sort of is plausible? Okay, so, and this turns out to be the typical picture. If you take any typical point xt and you look at the geodesics going down to -1 and 1, typically the geodesics will actually share the journey for a bit and then eventually sort of bifurcate. Okay. So for any point xt, it will be true that locally all the points will eventually sort of coalesce, and then eventually, so basically this is sort of the picture. So take any point xt typical, and then take some neighborhood of xt. So it will turn out that all the geodesics from points in this neighborhood will all meet at some point, and then one of them will, and then they will sort of, something is happening with my iPad, sorry. Yeah, so as this picture indicates, typical behavior is like you have -1 and 1, and you have some point xt, and you have some neighborhood of xt. And if you look at any point in the neighborhood, and if you look at geodesics, they will all sort of coalesce. They will continue for a bit, and then one of them will, and so then they will sort of go to -1 and -1 because they are in different locations. Okay, so all of them will share their journey initially and then eventually bifurcate. Now it turns out that this has some useful consequence in terms of the difference profile. This actually implies that the difference profile is locally constant. You see, because if you took the weight from xt to 1 and you took the weight from xt to -1, the difference, this initial segment would get canceled out because that actually appears in both this path and this path. And so the difference would be simply the weight of this latter, the second half of this path, which is marked in blue, minus the second half of this path, which is marked in purple. And this second half is going to be the same regardless of which point you're starting with. For any point here, they will all pass to this junction point. So the initial segment will get canceled out when you take the difference, and the difference profile will only sort of encode the difference of this blue part minus this purple part, which is a constant for all the points in this neighborhood. So that's actually an important observation. So is that point clear? Because that will be actually something that we'll continuously rely on. Like if you have coalescence, that tells you that the difference profile is locally a constant. Okay, so this is a crucial observation. Okay, so here is another sort of property of dxt, which is actually significantly more non-trivial. So the fact that, and this is sort of a very remarkable fact, and it's not obvious at all. So it turns out that if you fix t, so let's say take t to be 1. Take t to be 1, so height 1. And let's say I look at dx1 as x varies on this line. Okay, so it turns out that that function, that's a random function now, that function is monotone in x. And that's actually not at all obvious why that's the case. So here is a proof, but I don't want to get into that proof because I don't think, so I can come back to the proof at the end of the talk if I have time. But that's something that is not super difficult to prove, but it's certainly not obvious. I'm like, once somebody states that this fact is true, then maybe one can try and prove it, but certainly one would probably not expect it initially. Okay, so it's monotone. Okay, so this actually allows us to sort of adopt some perspective. So you see that if you have a monotone function, which is locally flat. So I said something. So I said dxt is typically locally constant, but it's also sort of monotone. So if you plot the function of dxt for any fixed t, the graph is going to look something like this. Okay. Now, any monotone function induces a measure on R. Okay, so it's a random measure for any fixed t, dxt, so this function d dot t corresponds to a random measure, right? So given any monotone function, it sort of naturally induces, you can think of this as a distribution function of some measure. Right? That's basic measure theory. So you can try to understand this random measure that this monotone function corresponds to for any given t. So it turns out that you can also sort of use this thing to construct a two-dimensional measure, but let's sort of ignore that for the moment. So let's not focus too much on this part, but this is an important sort of perspective. So this random function, we should think of it as a random measure, corresponding to a random measure. Okay, but importantly, this random function is locally constant almost sheerly. So as I said, so d is this locally constant function, and it induces a random measure. So it's plausible that this measure is supported on some fractal set. So the support should be a smaller dimensional set. Okay, so as for example, for people who are familiar, if you look at Cantor set, the classical Cantor set, that's so you can look at, so that actually induces a natural. So if you look at the natural measure that is supported on the Cantor set and look at its distribution function, that will actually also have the similar properties, that it's going to be locally constant, however, it's monotone. So the distribution function will again look like this. So it's mostly flat, but there are small parts of the real line where it grows. And this small part is actually a very sparse set, and we want to understand how sparse it is. And a way to sort of quantify sparsity is by their dimension. So for people who are not very familiar with this, so there are various notions of dimension. What we will talk about, or the result that we'll state, will be in terms of Hausser dimension. But at least sort of in your mind, you can sort of think of roughly this sort of notion that suppose you have a very small set, and let's say you take a very small subset of the real line, and let's say you pick a very small epsilon. Now you want to say how many intervals of size epsilon are needed to cover this set. Okay. So if you have the full segment, then the number of intervals of size epsilon that you will need to cover the full segment is of course 1 by epsilon-ish, which tells you that the dimension of this segment is 1, because it's 1 over epsilon to the 1. However, you can also, for the Cantor set, for example, you can construct such that you will only need 1 over epsilon to the 1/3 many such covers, which will tell you that the Cantor set has dimension 1/3. Okay. So this will be sort of this is sort of a coarse notion of dimension, and the actual notion that we'll sort of present our results in is significantly more complicated, but this is basically what it means. Okay, any questions so far? So what we have is, we have seen that this sort of the difference profile, if you fix the time coordinate and vary the spatial coordinate, then it sort of traces out a random monotone function, which is almost really flat. So it gives you a random measure, and so we want to understand what is the support of this measure, what is the points of increase of this random function. Okay. So here is a post result in this direction, which was obtained with Basu and Hammond in 2019. So we show that this fractal set, so NCD is the set of the support of this random measure. Okay, the set of points of non-constancy. So again, I'm pretty sure people already sort of understand what this means. So if you have some function like this, you look at NCD, a point X is in the non-constant part of this function if it's not locally flat around that point. Okay, this is literally the points at which the function sort of increases. So this result says that this sparse set has Hausser dimension 1/2. So in the previous language, essentially what this says is that if I take the real line and some segment and look at the sort of points at which the function sort of grows, I would need roughly 1 over epsilon to the 1/2 many intervals of size epsilon to cover the set. Okay, that's what this result says. So any questions about the statement of the result?
Yes, I have one. Can you remind me what the assumptions on the sheet? Is this just for the area sheet, or?
Yeah, I mean, we are working with a landscape whose height 1 marginal is the area sheet. Yeah.
It is the area sheet. Okay.
The area sheet, but soon we will get to the landscape. So we will sort of also vary the time direction. So if you don't vary the time direction, then it is indeed the area sheet. Yeah. So as I said, let me go to a previous slide. So yeah, so you see that once I sort of fix, if I fix my height to be 0 and 1, then I have a 2-dimensional process SYX, right?
Mm-hmm.
Then this is actually what is known as the area sheet.
Okay.
However, more generally, we will consider also when this temporal directions are varied, temporal coordinates are varied, in which case it would be what is the landscape, which is a 4. So now you need 2 extra parameters, because in the area sheet, it's a 2-parameter process because you have fixed the time coordinates in these 2 points. But now if you also vary them in height or the time, then you will get a 4-parameter field, which is the landscape, digital landscape.
Okay. Will you be discussing more general than the area sheet?
No, so somehow the point is, so the point of the talk is to say what this, the area sheet or the landscape is exactly supposed to be the scaling limit of all these integrable models, all the sort of LPP type models. And what we have, the results that will sort of present mainly will be for the landscape, which means that you should expect similar versions for the discrete and for all the pre-limiting models like the discrete and the semi-discrete ones.
Mm-hmm. Okay, thank you.
Yeah. Sorry, where was I? Okay, good. So this tells you that at least in this sort of, as was pointed out, like if you look at this area sheet or what this sort of, whenever you fix the height or the time coordinates and vary the spatial coordinate, then the difference profile traces out a random distribution function whose support has Hausdorff dimension 1/2. Okay. So recall that I said that it's almost really flat because of this coalescence type picture. So right, so points, nearby points, actually they all meet, and then they eventually go on to their journeys. So this picture is what makes it locally flat. So if you have a picture like this, that would actually imply that the difference profile on this interval will be just a flat line. So which suggests that if you want to understand the support of this measure, which means that where it does not look locally flat, then you should not see this picture, right? So which means you should see this picture instead. Like if you have a point and the geodesics actually don't meet they don't share their journey. So they immediately bifurcate and they go on to their separate journeys, right? So if you have this, it's locally flat, which means that if you're not locally flat, you should look like this. So in particular, you sort of can consider the set of Z of points Y upstairs, which admit 2 disjoint geodesics going downstairs. So you can speculate whether this set Z is exactly the support of this random function. So whether this set, which is the support of this random distribution function, which has Hausdorff dimension 1/2, is related to this set of points which admit disjoint geodesics. So this is indeed turns out to be true, and this was proven in a follow-up paper with Eric Bates and Hammond, where we show that almost surely the 2 sets are the same. In other words, it says that the support of this random measure is precisely the set of points admitting disjoint geodesics. Okay, any questions about this? Okay. Okay, so just to sort of carry on this discussion further, so what we have seen so far is this sort of random distribution function. So this difference profile gives you if you vary at least a spatial coordinate and fix the time coordinate, then it gives you a random fractal measure whose support has dimension 1/2. Okay, so it's a classical fact. There's another sort of canonical object, which is a subset of the one-dimensional of the real line, which also has dimension 1/2, which is that the 0 set of Brownian motion. So suppose you have the real line, and let's say you start a Brownian motion, standard Brownian motion started from 0. So if you look at the set of points at which the Brownian motion is 0, I mean, this picture is, of course, a cartoon of it. It does not resemble in the reality. So this set, I mean, in the picture, it looks like a discrete set, but it turns out that this set of zeros of the Brownian motion also is 1/2 dimensional. And that's a very classical fact. Okay, so now we have this classical object, and we have this new object, which also has dimension 1/2. And so you can speculate whether there is any connection between the two. Okay. So it turns out that there is indeed a connection, and to define that, so let's define Brownian local time, which is basically, which is basically a random measure supported on these blue points. Okay. Okay, so what is Brownian local time? So B is the standard Brownian motion. So local, so again, I should have used a different L here because I used already one L for the landscape. But let's say, okay, for the moment, let's just ignore that fact. So LT is going to be a random function, which is essentially which will be a sort of increasing function, which will be supported on the 0 set of Brownian motion. So how do you actually rigorously define it? So you said, let's say, take this integral of 0 to t, the occupation measure of Brownian motion in an interval of size epsilon. So which means that you have this real line, and let's say you draw a tube of size epsilon, a 2 epsilon, and you see how much time Brownian motion spends within this tube up to time t. Okay, so that's this object in the numerator. So the amount of time Brownian motion spends within an interval of within a tube of width 2 epsilon up to time t, and then you divide that by 2 epsilon. And it send epsilon to 0, it turns out that this thing will have a limit, and that limit is what you call as the local time. Okay, so this local time is a classical object. It's known that it's a random measure. Again, if you plot this function, again it will look something like this. So it's going to be mostly flat because Brownian motion is mostly non-zero, and the points of increase will be basically where Brownian motion is 0. Okay. So we have now two objects, both of them look similar, and both of their supports are 1/2 dimensional. So you can ask whether the two objects are related. And the point is, like the previous papers that I mentioned, or the previous works that I mentioned with Basu and Hammond, and then follow-up work with Bates and Hammond, the arguments actually did not provide any insight into this question, into how to what the answer to this question was. Okay. So is the question broadly clear what the question is? So I have two objects, one of them very classical, the other one quite new, and then they have some similar properties. So it's natural to speculate that there's a deeper connection. So it turns out that there is indeed a connection, and what we again, the statement is somewhat technical, but let's not stare too much at it. But what it simply says is that this process that we drew, the difference profile, if you look at the increment of that process, that's absolutely continuous with respect to Brownian local time of a particular rate. So again, the precise statement is not super important. The point is like the thing that we constructed from the landscape, which looked like which is this random measure or its distribution, that is absolutely continuous with respect to Brownian local time, which means that this 1/2 dimensional support and everything will certainly get carried over. Actually, much more is true, which this theorem does not state, and we proved it in that same paper, is that if you look at this process, the difference profile D, and if you in some sense take the local limit of the difference profile, you actually get exactly Brownian local time. So in a macroscopic sense, the difference profile is absolutely continuous with respect to Brownian local time. But if you take the local limit suitably defined of the difference profile, you actually exactly recover Brownian local time. You don't have any absolute continuity anymore. It's literally the same. Okay. So it turns out that this result was also independently and simultaneously somewhat later proven by, actually not simultaneously, but somewhat later proven by Duncan Dauvergne. Okay, is the statement broadly clear? So you have two functions. Both look similar. This is the Brownian local time. This is the difference profile, at least when the coordinate is varied separately. And it turns out that the increment of this process is absolutely continuous increment of this process. Okay. Questions? All right. And so this is joint work with Milind Hegde, who was my former student, He's currently a postdoc at Columbia. Former student jointly with Alan Hammond. Okay, so, but it turns out that so far we have been looking at this process when the time coordinate was fixed. So in the example that I sort of stated, t was actually fixed to be 1, right? So we took this difference profile, -1 and 1 downstairs, and then the dxt, the process was only sort of the spatial coordinate was the only thing that was varied. T was fixed to be 1 in the previous results. I mean, like t can be taken to be any fixed number. The process is the area sheet of the landscape is sort of scale invariant. So anything that happens for t equal to 1 will also happen for any given t. But the point is like t has to be fixed for those arguments to be true. And those arguments really sort of rely very crucially on the fact that this function is monotone. Okay, so as I have been sort of saying, the function looks something like this. So this function is monotone, and that's actually extremely useful, or actually extremely crucial in the arguments here, in the previous set of works that I mentioned. Okay. So let's now look at the temporal direction. This sort of goes back to the question that was asked. So the area sheet is when you sort of fix the two heights, minus, let's say 0 and 1 as the heights. But the landscape allows you to vary the temporal direction, temporal height as well. And so now let's look at the difference profile, again, from -1 and 1 at height 0. But let's say now when the point is varying along this line. So now let's say we are just sort of looking at the process D0, comma a variable. So D0t. So you vary the point on this line. And then from any point here, again, you look at this picture, you take the geodesics going down to -1 and 1, and you look at the difference of their weights. So that's a function that now lives on this vertical line. Now you see that this process is not monotone. It cannot be monotone because the expectation of this process is 0, right? This process is the difference between this weight and this weight. But these two things are symmetric because of the obvious symmetry in the picture. So this process for any t has expectation 0. So expectation of D0t is 0 for any t. Okay, so which means that this cannot be a monotone function. It is not. And so it turns out that the previous arguments actually don't work. And so it's not clear what is actually going on here. And so this was sort of open for a while. And so this is what I just said, previous arguments fail. So it turns out that one can actually analyze it, but one needs a completely different perspective. And so this is sort of ongoing work. I'm like, the paper is being written up and should sort of hopefully be up on the archive sometime in the near future. So we ask the same question, let's say, again, so the local constancy is going to be the same. So this function, if you plot along this line, it's still going to be locally constant, again, just because of coalescence. But the function is not going to be monotone anymore. So it might, if you plot the function, it might look something like this. I'm actually now switching, instead of varying it in the vertical direction, I'm just sort of plotting the function in the horizontal direction. It will look something like this. Okay, so it's still locally constant mostly, but now it's not monotone anymore. It can increase and decrease, and you can try to understand what is the Hausser dimension, or the dimension of the points at which it is not flat. Okay, so it turns out that this dimension is now 2/3 instead of 1/2. So when we varied the point in this direction, the support had dimension 1/2. When we vary the point in this direction, the support has dimension 2/3. So at this point, the dimensions don't make much sense. Where are these numbers coming from? Where is 2/3 coming from? Where is 1/2 coming from? So I'll eventually sort of hopefully give some idea of what is the source of those numbers. But one thing to note is that the behavior in the temporal direction is different from the behavior in the spatial direction. Okay, so is the statement clear? But just to make sure, is it a 50-minute talk or an hour talk?
Yeah, it's usually 50 minutes.
Oh, so then I'm running a little behind on time. So how much time do you have actually?
Yeah, you have 5 minutes.
5 minutes, okay. Okay, so again, so in the analysis of this temporal behavior, we actually construct a novel version of the Brownian local time in this setting. So what we construct is sort of the geodesic local time. By the way, so just forgot to mention, so the previous result is shared with Lingfu Zhang. This is with Lingfu Zhang, who's a current student at Princeton with Alan Sly and is joining Berkeley as a postdoc this coming year. So what we construct in this analysis, so one crucial ingredient in the analysis of this is what is known as the geodesic local time. Again, this you don't have to stare too much at the slide, so let me just move up. So we look at some geodesic. Actually, for convenience, we actually look at something called the semi-infinite geodesic, but the endpoint is, one of the endpoint is 0, the other endpoint is not fixed. The other endpoint is simply, you can think of it as infinity. So this is a geodesic which basically goes vertically up towards infinity. Okay. So now you can look at the points at which it intersects the vertical line y-axis. So this can be thought of as a geodesic version of Brownian local time, right? So if this red curve was Brownian motion instead, then the zero set would be literally the zero set of a Brownian motion. So here we're looking at the zero set of a infinite geodesic. So it turns out that you can define a version of local time for this random set as well. And so this was constructed in this sort of ongoing work with Lingfu. So unlike Brownian local time, which unlike the zero set of Brownian motion, which has Hausdorff dimension 1/2, as I just said, this zero set of the geodesic has Hausdorff dimension 1/3. Okay. So this is actually a novel object that actually is very crucial in our analysis. Any questions about the object?
So here you are dealing with a limiting vertical geodesic.
Yeah, so there is a way to take local limits. So you can, like a version of this will also be true if you take a finite geodesic, but let's say you start at 0, okay, and now you end at n comma 0 comma n, okay. And now you can, so there is a way to take a local limit of these paths as n grows to infinity, and this will give you some infinite object that grows essentially vertically.
Okay, thank you.
Okay, any other questions about this? All right, so this turns out to be a key object, and again, this exponent might not be very clear, and then maybe, okay, so let's see. So okay, so I don't have too much time. So these are basically some of the results. So let me just quickly sort of talk a little bit about where these exponents are coming from. Okay, so I'll mostly, so the temporal arguments are quite complicated, so I'll probably not get time to sort of talk about that, although I'm happy to chat offline if people are interested. But let me just sort of give you the basic reasoning behind the 1/2 dimension in the spatial direction. So recall that, as we said, like if something is locally coalescing, if you have a picture like this, if they coalesce, then you don't see anything interesting, and then the difference profile is flat. So for you to see non-flatness, you better have a picture like this, where you have points x and x plus epsilon upstairs, so that the geodesics going down to -1 and 1, they don't meet at all. So it turns out that this probability can be actually computed roughly, and this probability turns out to scale like, so you see that this interval has size epsilon. So it turns out that this probability scales like epsilon to the 1/2, and this relies on some earlier work of Hammond using Dyson Brownian motion. So I don't want to go too much into this, but it turns out that this probability can be computed. Okay, the probability that this geodesic and this geodesic don't meet. Now using this, you can get a dimension upper bound. You see that if you have this interval and you want to see how many small intervals of size epsilon are needed to cover the set of points at which the function has some growth. So let's say the function grows somewhere here, stays flat, grows somewhere here, stays flat, grows somewhere here, and stays flat. So in this picture, you need 3 intervals to cover the points of growth of this function inside this segment. However, as we have seen, for this to have some growth inside this interval, the geodesics from the endpoints of this interval cannot meet. But we know that the probability of this happening is epsilon to the 1/2 from the previous slide. Okay, so that means that, so there are 1/epsilon intervals. Each interval exhibits a behavior like this with property epsilon to the 1/2. So the total number of intervals that survive is 1 over epsilon times epsilon to the 1/2, which is epsilon to the minus 1/2, right? So this tells you that you can certainly cover your set of growth by at most epsilon to the minus 1/2 intervals. Is that argument clear? How you go from the probability of non-coalescence to an upper bound on the number of intervals that you need to cover your set of growth? Okay, so as I said, so this tells you that the dimension is at most 1/2. It could be even smaller. It's sort of a crude bound which says that you can cover everything by at most this many intervals. Okay. So I think I'm almost out of time, but let me just spend the last negative minute on the lower bound argument. So the lower bound is different. So the lower bound actually uses the fact that this process that I said. So if you look at the Airy process, so remember, if I just had one point and traced out the passage time as a function on this line, the function looks like a parabola with some perturbation on top of it. It turns out that this perturbation or this function itself on compact sets looks pretty close to a Brownian motion. Although at any given point, the height, the fluctuation is non-Gaussian. It's given by this Tracy-Widom distribution. If you look at the increment of this function, is close to a Brownian motion. And then proving how close it is to a Brownian motion has been an object of much study because it has many applications. And so there are various results in this direction. One strong result was proven by Jake, Calvert, Alan Hammond, and Milan Hegde. Previously, there was results by Ivan Corvin, Alan Hammond, Jeremy Kostel, and Remenick also had similar results. So there's been a whole sort of series of results which tries to compare this Airy 2 process to Brownian motion. But we will see what the implication of that is. So you see that in our context, you have these 2 points, and we are considering the 2 sort of functions centered at these 2 points. Both of them are like locally Brownian. Okay. And now I'm taking the difference, right? So the difference profile is essentially the difference of these 2 functions, right? That's exactly the difference profile. Each of these functions are individually like Brownian motion. So in particular, they are 1/2 Holder regular. Okay, so the regularity of these 2 functions is 1/2 Holder, which means that the difference is at least as good, right? So it should be also 1/2 Holder regular. It could be even better, but certainly you get a 1/2 Holder regularity from the individual 1/2 Holder regularity of these individual processes, and that comes in through comparison to Brownian motion. Okay, so you see that this difference profile is mostly flat, but it's also 1/2 Holder regular, which means that if it grows inside a small interval of size epsilon, it cannot grow by more than epsilon to the 1/2 because of Holder regularity. However, you can show that this function actually overall grows linearly. So because it's essentially, and that is actually not very hard to see because it's a difference of 2 parabolas. You can that's a sort of simple calculus exercise is that if you have 2 parabolas, algebra exercise centered at 2 different points, if you take the difference, it's going to be a linear function. Okay. So this difference profile is locally flat, but globally like a linear function and also locally a 1/2 Holder regular. So which means that if it has to grow by, let's say, amount which is order 1, let's say it grows by amount 10 in some interval, it's mostly flat, it's not growing mostly, but whenever it grows in an interval of size epsilon, it should grow no more than epsilon to the 1/2. But overall, it has to grow by value 10. So it should so the number of intervals where it should grow should be at least order epsilon to the minus 1/2. Okay, so this tells you that the lower bound is also true. So is that logic clear? How local Holder regularity and global linear growth tells you that the growth rate, the number of intervals that you see, where the number of intervals where you see some growth is at least epsilon to the minus 1/2. So that proves a lower bound. However, you can do the same thing in the temporal, and so this is going to be the last slide. So you can play the same game in the vertical direction, in the temporal direction, and you can use coalescence to prove the upper bound. You can use this Holder regularity to prove the lower bound. So it turns out that the upper bound will be 2/3 in that argument, and the lower bound will be 1/3 in the argument. So you see that in this argument, in the spatial direction, both the upper and the lower bound, the arguments matched and gave you the same number, which is 1/2. However, if you do the same thing in the temporal direction, the lower bound actually does not match the upper bound. And that's because the function is not monotone. So the lower bound argument that I sort of indicated in the previous slide does not capture cancellations that this sort of process sort of exhibits, because it takes both positive and negative values. So you need a new argument to get a matching lower bound. So the upper, so as a result indicator, the 2/3 is really the truth. And what you have to do is to improve the lower bound. And usually proving lower bounds for Hausdorff dimension is the harder task. So you need new arguments to boost this lower bound from 1/3 to 2/3. And that's what this recent work with Lingfu captures. So I'm like, I don't want to get too much into this, so I'll just stop here. Yeah.